Hello and welcome back. We're coming to you tonight from the old station downtown. This used to be the hub of activity of the city. This presentation 8-9 is part 2 of a series in alpha and beta errors in statistics. The material is in your workbook on these pages and your textbook. We want to acknowledge the development team of Brad, Spencer, and Amanda. We ask that you pause the screen and read the material on the screen. We're testing a drug with a potency of 5.00, and we want to detect or know if the potency is significantly above 5. So we're setting up the null hypothesis here. The mean is around 5.00. The alternative is greater than 5. And we want to look at the various types of errors encountered. Now, this information on the screen was in the previous video. It's a one-tail, right-tail test, alpha 5%, Z critical, your X bar critical given here, 5.037, critical cutoff for X bar. And to the right we're going to reject H0, to the left fail to reject. And this is called the correct decision on the left of this red line. Probability of that happening is 95%. And on the right here we have type 1 error, probability is 5%. So under these circumstances, if H0 is actually true, this will be a correct decision with probability 95%. Type 1 error, the probability of rejecting H0 when it's true is 5%. Now we're going to look at the case where this is false, and in this case we want to test mu equal to 5.05, standard deviation or the standard error 0.0227, and that's coming on the screen here now. Now this this red region is your beta error. And to calculate that error, we take the cutoff, or the critical X bar value, minus your hypothesized value, 5.05, divided by the standard error, and getting an area there of 28.3%. Probability of a type 2 error. Probability of correct decision is 71.7%. Now we also look at the case where we go to 80. Now, as you know, when n is equal to 80, this sampling distribution becomes much narrower. And that's the point here. The standard error is now 0.013. We're going to do a table of that shortly. Critical value 1.645. X bar critical 5.021. And feel free to pause the screen at any time and write these values down. On the left we fail to reject. On the right we reject H0. So if H0 is actually true, mu is equal to 5, and we accept it as true, this is a correct decision with probability 95%. On the other hand, if we reject H0 when H0 is true, this is a type 1 error, and this probability is 5%. Now we're going to look at the case where mu is equal to 5.05, and this hypothesized value appears wrong. We're saying this curve is now situated at mu equal to 5.05, standard error 0.0134. Now this criteria line connects the two. It's the same for this test. And on this case we see on the left of this line we're going to accept H0 as true when it's false, and this is a type 2 error. On the right we're going to reject H0 when it's false. This is a correct decision. We need to find that area of this tail here, the critical X bar value of 5.021. We're computing that value now. The probability of getting a Z to the left of 5.021 is 1.3%. And this suggests that because we bring the sample size up to 80, we reduce our beta error quite dramatically. Now we're going to look on the screen here at this table of values. We're going to plot these values. Now for n equal 28, the type 2 error is 0.301. It's up here on the screen. Here they come on the screen now. So these are just summary values of the previous screen. And there's your beta error there. And for n equal to 50, we've calculated that. Here they go. You can see that the beta error has dropped now to about 10%. If we go to 80, the beta error is 0.013, and here it is on the screen now. 1.3% error simply by taking the sample size up to 80. Now we're looking at as sample size n increases, the standard error decreases, critical values decrease, they fall back towards 5, and the z-score continues to decrease into the negative region, and the beta error decreases quite dramatically. Now here is the screen. It's a graph, beta on the vertical axis, sample size n on the bottom axis. We're saying if we specify a particular value of beta, for example, less than 0.05, come across here to this graph, come down, that will suggest the sample size we need to employ to reduce the beta error to this 0.04. And up here you can see that we can change this whole table by taking mu equal to 5.06. And what happens is 5.06 means this curve moves out with the beta error getting smaller and smaller. Well, that's the end of presentation 8-9. We ask you to review it once again and go to presentation 10.